Hello, my name's Ian, and this is the first of a series of videos about a new project I'm starting. I've been inspired a bit by Chris Gamble of Contextual Electronics, and Chris has pioneered this really interesting project-based approach to learning electronics that I like a lot, and I thought to myself, well, why not give it a go? I'm a relative beginner in electronics, so some of this might be a bit dodgy, but I do have a lot of software experience. I've been working as a programmer on and off for 25 years. So there's a good chance of us being able to do some more sophisticated things in terms of software. We'll see how it goes anyway. So what's the project? We're going to build a little robot that's able to sense its environment and make a map. And I'd also like to put a pen on this thing so it can do some total graphics. And I'd also like to be able to control it directly using a game controller attached to a PC. And the reason for picking this project is it's a mixture of things that I've got a reasonably good idea how to do and some things that I have no idea how to do at all. And I'm going to try and do things in a way that give the biggest bang for the buck in terms of learning, which means sometimes doing things in a slightly awkward or unusual way. Anyway, we'll see how it goes. I'm going to start with doing a little bit of functional requirements for this thing. And that sounds very formal, but it's really just a way of thinking about what we're going to do and where we're going to start. So there are three main parts of the functional requirements for this. There's mapping. And what this means is I want to be able to put the robot down in a room and it drives around, senses where the walls are, and it makes a map. And the functional requirements for the components of the robot flow pretty naturally out of that. These other two requirements, turtle graphics and direct control, they have a few other implications as well. Turtle graphics in particular requires pretty precise positioning. If you want to draw a circle and have the circle close up when you get back to where you started from, your motor control for your robot needs to be pretty good. And to be able to control the thing directly with a game controller attached to a PC, you need some form of communications as well. Now, because this is a learning project, there are some functional requirements that go with those, non-functional requirements that go with those functional requirements. For a start, I want it to be cheap. I want it to be easy to assemble and easy to test. And that means not using any ridiculously small parts, like tiny, tiny components. I want it to be easy to program using all free tools. The other two non-functional requirements here probably deserve a bit of comment. Your idea of fun and my idea of fun might be pretty different. But what I mean here is that I want to do things in a way where I can dig into some of the details of the electronics. There are so many integrated modules around now that you could build a robot like this very easily just by plugging modules together, pre-built modules together. And if you want to get quickly to the point where you've got a robot where you can do some software experiments, that's the best way to do it. If you want to learn how this stuff works, you need to dig in a bit deeper. And that's what I'm going to try and do here. It might mean doing some things that look a bit weird, but hopefully they'll be educational. Then there's no such thing as cheating. As far as I'm concerned, as long as you're learning some electronics or embedded software, the sources you use don't really matter. It's fine to take designs from application notes. It's fine to ask people's opinions about stuff or just ask for help. It's fine to copy code from Stack Overflow answers. It's all fair game. As long as you come out of it knowing more than when you started, then that's all to the good, I think. So, we're going to build a robot. A robot's not just some electronics, it's a physical thing. So you need some physical framework to hang your electronics off. I did originally think about making a robot with a PCB chassis. So the robot would basically just be a PCB, and you'd attach motors and encoders and sensors and all the electronics to the PCB. And that would have been fine, but I did some calculations, and it looks like that would actually be more expensive than just buying a chassis, because there's some very cheap chassis around, and if you end up making a few spins of your boards, then it's better to make them small and just have the electronics on them rather than using the electronics as a chassis as well. So I've picked a chassis, and I'm going to go with this basic two-wheel design that is pretty common, just because the mechanical aspects of this are less interesting to me, and so I don't want to do anything too weird here. So you've got a chassis and you've got two wheels. You need motors to drive the wheels, obviously. But you generally also need an arrangement of transistors of one kind or another to route current to the motors. And there are integrated solutions for this, but there are still some interesting points to think about with it, like how you do PWM control for motor speed. Braking might be quite interesting. And yeah, I mean, there's a few things to think about. Like I might try doing some current sensing to measure torque on the wheels, that kind of thing. So you switch your motor driver on, it makes the motor go round, but you don't know how fast it's going or how far you're going. And if you want to do any kind of precise control of position, you need a feedback loop to measure the distance that the wheels have turned. And there are a couple of different ways of doing this, but I'm going to use a simple optical encoder system. But even there's some interesting bits with the electronics, and there's some the software side of it shouldn't be too complicated. But again, it should all be kind of fun. And so to drive your motor drivers and to process the data from your motor encoders, you need a microcontroller. And I'll go for something pretty vanilla with this, I think, an STM32, mostly because I have a development board lying around that I can use for early experiments. One of the things I want to do is this idea of having the possibility of just driving the robot around with a joystick or game controller attached to a PC. And that means that the robot needs some way of communicating with the outside world. I've got some fun ideas with this. I'll talk about it in a minute. For the technical graphics, you need a way to pick up and put down your pen. And I'm hoping that I'll be able to find a simple latching solenoid solution for this, something like that. For mapping, you need sensors. You need to be able to see where the walls are. For this, I'm going to use some ultrasonic sensors. And to be honest, I'm actually a little bit clueless about how to do this. So there's going to be a bit of a science vibe to this part of the project where I do some probably quite extensive experiments to see how it'll work. As one extra little sensor, I'm going to add an accelerometer to the board. And there are a couple of reasons for doing that. One, there are quite a lot of integrated MEMS accelerometers around that have I2C or SPI interfaces. And so I've never actually built or interfaced an I2C or SPI device to a microcontroller. So that's something that everybody needs to know how to do. So it's a good thing to experiment with. An accelerometer is also handy for telling you if you bumped into something. But I also think that I could be able to use it to help with the positioning. Either just having a simple signal saying, hey, we're moving, but also possibly doing some sensor fusion with fusing data from the accelerometer with the odometry data you get from the motor encoders to improve the precision of the positioning. So that could be quite interesting. And then all this stuff needs power. And for simplicity, we'll probably use a lithium-ion battery, charging from USB, as you do. Nothing very complicated there. There'll probably be two power domains, one for the microcontroller and any other logic stuff, and one for driving the motors. There might be other power domains for radio and the sensors and things, but I'll deal with that when we get to it. So physically, the thing will probably look a little bit like this, looking down from the top. The reddish, pinkish, circular thing is the chassis. You have two wheels. There's a caster at the back to balance the thing. The battery is behind the center of mass to make it a bit stable. And you have a PCB on top with a hole in the middle for a pen, some sensors, motor drivers, encoders, power, all that stuff. The motor encoders are, here they're shown as using discs, like interrupter discs, attached to the motor outputs. And there are photo interrupters that stick out of the bottom of the chassis attached to the bottom of the PCB that interface with those. The chassis I'm going to use is this one from SparkFun. It's super simple, basically 2 aluminium plates, a bit of hardware to attach them, a couple of motor mounting brackets, a couple of wheels. It should be good enough for our use case. And the other thing is that it's very easy to modify if you need more mounting holes for anything. There are quite a lot of holes on there already, but we might need to put some somewhere else. And this is what it looks like when it's put together. I mean, ours will look very much like that with just a PCB on top rather than a breadboard. There are some motors recommended to go with this, and I'm just going to use what people recommend. They're cheap, brushed DC motors with plastic gearboxes, plastic reduction gearboxes. They're easy to drive. I mean, they're not super robust or anything, but they'll do the job. So that's the hardware. I'm also very interested in the software, and I'm going to talk now about 4 milestone projects that I'd like to do with this. There are going to be lots of experiments and testbed things along the way as well. So the first one of these is direct control with a game controller attached to a PC. So to do this, you need to get the motor system working a bit. It doesn't need precise positioning or anything, but you need to be able to make the motors go. And you need some form of communications. So this is a fairly simple test of the motor control system, and it will be a good indicator that communications works all right. Then there's Turtle Graphics. Now, Turtle Graphics is this idea that you give commands to your robot. You say, go forward 50 centimeters, turn right 90 degrees, do it again 4 times, and it drags a pen around on some paper you put on the floor, and it draws pictures. And that's a simple idea in principle, but it's a very good test of the precision of your motor control and your positioning. Because if you want to draw a closed square and you're off by 5 millimeters when you get back to where you started, it's really obvious that there's something wrong there. So that's a good test of that. And the other bit of the software for this is a little interpreter for some language to tell the robot how to drive around. And it's traditional to use Logo for Turtle Graphics, so I'll probably do that. Then we get to mapping, and I've split this into 2 parts. The first thing I'll probably do with this is to use a standard mapping algorithm, some software that already exists for some algorithm like SLAM or something. Run that software on the PC, and just have the robot send sensor data to the PC and have the PC send back commands to the robot to tell it where to go. That seems like the easiest way to get going with mapping. Eventually, though, I want to have autonomous mapping on the robot, and that'll probably have to be done in a different way. And I've got some interesting ideas about this. They're very vague at the moment, and the word safety monitor plus ML, which is machine learning, stroke GA, which is genetic algorithms, are supposed to be a vague pointer in that direction. But I'll have to see how we go with that. So there's obviously a lot of stuff involved in this project. You could go on the SparkFun website and buy a robot like this for $20, probably better than the one that I'd make. But doing this from scratch is quite a lot of work. And so it's quite difficult to know where to start. I've got 3 prototype-like sub-projects I'm going to do, one for each of the subsystems that I feel least comfortable with. First of all, there's the motor driver and encoder stuff. And the electronics for this I feel reasonably confident about, because what I want to do is very similar to what was done in one of the contextual electronics courses. But then the software side of it is interesting, because you want to do odometry, so measuring the distances that things go. You want to do that quite precisely to be able to get precise distancing. You want to be able to drive in curves, so you want to do circles. You want to be able to, say, drive forward at this speed, turning left on a circle of radius 1 meter, that kind of thing. You want to be able to deal safely with acceleration and braking, and that might mean things like measuring the torque on the wheels, using accelerometer data, having some kind of soft start to make sure that your movement's not too jerky, all that kind of stuff. So that's quite interesting. The second sub-project is about communications, and I could just buy an integrated communications module to use for this, either regular Wi-Fi or one of the low-power 2.4 gigahertz radio systems used for Bluetooth or Zigbee or things like that. But I don't want to do that for a couple of different reasons. First, I want to learn how to do some of the electronics for this. And that really means not using Bluetooth, because 2.4 gigahertz is probably a bit much for me at the moment. The second reason is that the software side of Bluetooth and things like it tends to be quite complicated. And for the software for the robot, I'd really like to try and take a mostly bare metal approach, which means writing my own drivers for the peripherals on the microcontroller, doing most things just by writing to registers. With Bluetooth, that's difficult because it's a complicated protocol. It's designed to cover a lot of different cases, and you're almost forced to use a vendor-supplied library for it. And I really don't want to do that. So I was looking at other possibilities. I was thinking about using infrared, but I wasn't really taken with any of the parts that I looked at for that. And then I read about this ISM 434 megahertz band. ISM is industrial, scientific, and medical, and it's the portion of the radio spectrum that's allocated to unlicensed use for those kind of applications. And this 434 megahertz band is, it seems mostly to be used for things like remote keyless entry for cars and garage door openers and things like that. But what I found is that there are some reasonably integrated transceiver solutions for this band that aren't so integrated that you just plug them in and you don't learn anything. And I think I could probably use one of those for this. So the idea is to build a thing I can plug into my PC, a USB dongle basically, with a 434 megahertz transceiver on it, and have it so that this thing can look like a normal Linux network connection. And so I got this idea from, there's an application in the OpenThread network stack that allows you to do this. You have a USB dongle with some 2.4 gigahertz radio enabled microcontroller on it. You flash some special software to this thing, and then there's a user space process that runs on Linux that makes this mesh network, this OpenThread mesh network, look just like a normal Linux network interface. And that's really interesting. I think it's really clever, and I'd like to learn how they do it. And this application seemed like a relatively easy way to do it, because it's a point-to-point connection between the PC and the robot. So the goal with this sub-project is basically to build a whole 434 megahertz radio stack, end-to-end, hardware and software. We'll see how that goes. It should be kind of fun. The third sub-project is about the ultrasonic sensors, and in principle, these sound really simple. You transmit an ultrasonic pulse, you time how long it takes to bounce back. Simple. But the details are a bit more complicated. First of all, you need to know how to drive your transmitter. You need to know what the pulse that comes out of the transmitter looks like. You need to amplify the return signal at the receiver. You need to detect the return signal at the receiver. It's not even clear to me whether you should only be thinking about measuring pulse transit times, or whether you can do things like get the texture of the reflecting surface by looking at the envelope or the amplitude of the return pulse. I don't know if you can do Doppler measurements for looking at movement. I don't know if you can do pulse compression with these cheap transmitters. So there's loads and loads of questions with this, and I'm going to have to do some experiments. So this is going to be a bit sciencey, I think. So that's what we're going to do, and I think it's going to be quite interesting. Some of the electronics will probably be pretty dodgy because I'm learning. Some of the software might be quite fun because I know a bit more about that. I'm going to aim to make a mixture of short videos, probably write some articles, write detailed annotated source code for any of the software. I'll put all the design files and software on GitHub, and any other materials I'll put on my website. Anyway, next time we'll start talking about motor control. See you then.